Good morning, everyone, and welcome to the Frontier. We're all having a good time? Yeah! Okay, well, we're about to be joined on stage by CCP Relativistic, talking about black holes and the physics of the frontier. So, warm hand, everyone.
Woohoo! Thank you, and welcome. Like CCP Bitboy told you, I'm CCP Relativistic. I am a senior software engineer here at CCP, working on eFrontier in the gameplay engineering team. But before I did that, I have a PhD in computational astrophysics from Aveiro University in Portugal, where I worked on numerical relativity and black holes. I've been at CCP for just over 2 years and only working on Frontier. So just to get right into it, because we all have a Frontier keynote to get to in 30 minutes. So I'm not gonna speed run through this, but we'll probably do it quite quickly. I just want to start by asking the question, what does it actually mean to invent a universe or create a universe for a video game? Because that's what we're trying to do. We're basically trying to come up with a way to determine where the game takes place and the map or the spatial relationships of the locations where the game takes place. Think about the map in EVE Online. You have solar systems, you have some stargates that connect them and stuff like that. So we're basically trying to come up with something similar, but now for eFrontier. Since Frontier uses the Carbon development platform, which is the game engine that runs EVE Online and Frontier, we're kind of bound by very similar rules as EVE Online. Like I told you, we have solar systems. There might be stargates that connect those solar systems, but we'll see once we get a bit further. The players play inside the solar systems, and then there's, they can jump, or they can take the stargates, or whatever methods we give them to move between them. The solar system follow like a hierarchy of being grouped into constellations and regions, which is also basically determined by the platform, as in the Carbon development platform. And like usually we think about constellation containing tens of solar systems, while regions contain hundreds of solar systems. I actually should have clicked a few times here. So basically, each solar system will then have to have a 3D coordinate. So 3 numbers that determines its spatial location, and then some star that has some stellar properties that might be its mass, its radius, its luminosity, and so on. And then some stuff inside the solar system that the star occupies, which might be planets, moons, infrastructure, stations, stargates, content for the player to interact with, and stuff like that. So I guess even before asking that question, oh no, Mr. Technical Man, I lost this thing. Yep, okay, in the pocket, nice, thank you. So, why do we even want to do this? Why wouldn't we just, Python has a really nice random number generator, we might as well just put random.random, get 3 numbers, place the systems like that, do the same for the attributes, and call it a day. Why don't we just do that? And I'm not saying that the reasons I'm about to give you are good reasons, but there are reasons, so hopefully you'll believe me and trust me. The first one is just the fact that EVE Online set the precedence 20 plus years ago. I don't know if you know this, but this is one of the initial simulations of the EVE universe and the EVE map. It was done by also a physicist back 20-something years ago, where he basically used something called diffusion limited aggregation, which is usually used to model crystal growth in physics and chemistry and stuff, and that was actually used to model the EVE Online map. The 3 empires were basically added as nodes for the crystal growth, and then it grew out, and like the nodes of the graph that the crystal grew to, I guess, represented the solar systems and the stargates and stuff. Obviously, the map has then been added onto, so you've kind of lost this sort of structure from the map, but that's the underlying initial structure that was there. eFrontier, I don't know if you've known this, but you'll definitely see it if you go to the keynote. One of the pillars of eFrontier is that it's grounded in science. What that means is really just that we try to think about the science behind the actual thing that we're implementing, our spaceships, the universe, and whatever we're doing, when we're making design decisions. That's not always possible, so I jokingly say that we go from the scale of being grounded in science to based in science, and then when we really break the rules, I just say we're inspired by science. And a lot of what I will talk about today is obviously just inspired by science. I'm not going to tell you when we're grounded, based, or inspired by, but you'll hopefully figure it out. Then we get to kind of, I'm not going to say out there reasons, but there is this idea that we're creating, especially because of the blockchain connection and all of that, that we're creating an immutable world that follows the physical laws of something. So if we simulate the world, we believe that the world will be better for the players that inhabit it because it follows some rules, that like underlying laws or rules that then gameplay systems and stuff emerges from. And the fourth point is really just that stated again. Yeah, okay. So what are we actually then going to generate and simulate? What should the world look like? And I know this is just a single slide that I'm going to tell you about, but you'll see a small Slack conversation between me and our creative director, CCP Maximum Cats. But basically, we know that the game has to happen in a galaxy, right? That's at least one of the fundamental assumptions here. And we know that galaxies come in a variety of shapes and sizes, and there's a few categories. There's elliptical galaxies, irregular galaxies, spiral, barred spiral, to name a few. But our narrative and game design directors, and actually our CEO, wanted something different. They've thought that like a single galaxy was a bit too vanilla, and the initial idea came from this Slack message. CCP Maximum Cats asks me, CCP Relativistic and CCP Wizard, or tells us that there is this idea going on to explore a key art with a trippy gravitational lensing overlap of 3 black holes. At this point, he also realizes that 3 is kind of out there. He says 2 we can probably pull off, yada, 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 but 3 is a bit more unique. I haven't actually found any good examples online. With that in mind, I have a question. Is this completely insane? Is there a way to get a simulation for the 3 black hole setup, even if it's very rough? And then there's some artistic ideas, like, okay, so you take 2 black holes, that's actually doable, and you can actually search for that. But 3 is a bit weirder, because then you start seeing images of the second and third black hole around the first one and so on. So it gets a bit more complicated. I answer shortly after, yes, this is completely insane, but let me look into it and think about it. And he says, Project Frontier in 2 sentences. Okay, a day later, you see this is February 8th last year. A day later, I have code, which I reused from my PhD code, which was basically doing ray tracing around single black holes. And I realized that I could kind of fake 3 black holes being in there and basically managed to ray trace, as in ask what happens to light when it travels around 3 black holes for this kind of space-time. This ended up being the key art that you've probably seen and you saw on the screen earlier, where there's like a big black hole and one in the accretion disk and one behind it. This ended up being the inspiration for that. So I did like a 36-hour simulation of ray tracing stuff around 3 black holes that we then gave to the artists, which made that picture and then video. So, but what this means for the world generation is that we now have a galaxy that has to have 3 supermassive black holes at its center. And I don't know if you went to Dr. Ronald Turner's talk yesterday or Dr. Becky's talk yesterday at the astrophysics one, or my talk on Thursday about black holes. But we usually only have 1 or maybe 2 that orbit each other. And usually the 2 that orbit each other, they're in solar systems. They're not supermassive. But gladly, in the last few years, we have actually observed galaxies merging. And we kind of knew that galaxies merge, but recently we've seen 3 of them merging. So here's a picture from NASA, I think, or ESA, where 3 galaxies are merging. You see the center of them all here, and you kind of see that their spiral structures or whatever structure they had before has kind of been disrupted, like tidally disrupted. Here it is in the X-ray. Here's another one, a bit more, I don't want to call it artistic, but a bit clearer, I guess. So you have 3 galaxies that are kind of smashing into each other. So our work is cut out for us. We want a galaxy that has 3 supermassive black holes at its center. We have to generate 3 galaxies. That's the first step. Or generate 1 and then generate 3 of them. And then smash them together. Simple, I hope. So first thing, we have to build a single galaxy. And we know that galaxies consist of a handful of building blocks. There's the bulge, which is like the central, somewhat spherical thing that is around the central black hole. There's a disk, which is whatever spins around it. And then there's a halo. The halo is actually the dark matter halo, which is just like a sphere of dark matter that is around all the other matter. I'm not really going to go into what the dark matter means or does, but we need to have it such that the calculations work. If you don't agree with that, you have to go to another lecture. And gladly, back in 1992, Lars Hernquist basically created a prescription to generate galaxies. What that really means is just he put forth a few probability density functions that you can sample from, and if you sample from them, you will get something that looks like a galaxy. So that's what we had to implement, and very gladly, yeah, here it is. While this approach is not fully rigorous, empirical tests suggest that it is adequate for studies of, where is it? Galaxies to imposed perturbations such as bars, as in it is adequate for studies of interacting galaxies. Basically what we want to do. Nice. Then we basically made the code to actually do this, put it in a computer, put a black hole at the center, and we get something like this. This is, does anyone know how many stars there are in the Milky Way? Billions, right? Try to put billions of points into any simulation that is not a supercomputer, and you run into problems. So we're not going to simulate a full-on galaxy. So I think this galaxy has like 6,000 stars or something. So obviously it doesn't look completely like a galaxy, but you know, you still see the structure, that you have sort of a bulge, you have the central black hole in the middle, and then you have some sort of disk-like structure. So we have to do this 3 times. We get a big black hole, a medium black hole, and a small black hole. This also took months to get out of our creative director. Asked basically, should the black holes be different? Should they behave differently? Should they look different? No one could give me an answer, so eventually I just did something, and they said, that looks fine. One of them is actually tilted, so these two actually lie in the same plane, and just like they will move toward each other, but this one is a bit tilted, just to create some interesting things, and you'll actually see it in the result in the simulation later. Then we have to calculate the forces, like how does each particle move? In order to do that, we have to calculate the force experienced by every single particle in every single galaxy. From that, we get the acceleration and then move it. Since we know the position and velocities of all of them, we're just missing the acceleration. We can calculate that from Newton's law of gravitation. But that's kind of, I'm not going to say it's a hard problem, but it's a problem that scales like n squared. Which really just means that if you have 10 particles, for particle 1, you have to do 9 calculations to find the force experienced by it. For particle 2, you also have to do 9 calculations, and so on up to particle 10. If you have thousands of particles, let alone tens of thousands of particles, that scales very fast up into a lot of calculations that you have to do. You could still technically do it, by the way, it would just take a long time. So there is something called the Barnes-Hutt algorithm. I'm not going to go into too much detail of it, but basically what it does is that when you're calculating the force experienced by one particle, you make the assumption that far away particles can be grouped together, and you can calculate the influence of maybe hundreds or thousands of particles by just finding the center of mass of all of those particles and the total amount of mass. However, the more you do this approximation, the more accuracy you lose. So there's a parameter theta that I'm going to draw up here in the corner, and then there's a number of calculations that I'm going to draw up here, and then there's a video where you basically just keep on splitting it. Each like quadrant here is basically being considered as a single particle, and we're calculating the force somewhere in this picture. And then you see as we decrease theta, we have to perform more calculations, but we get better results. So then balancing accuracy versus speed is basically just something like, are you willing to sacrifice accuracy for speed? If this were an actual physical simulation that we were then trying to observe in the universe or something, we would probably not want to sacrifice too much accuracy, but we're making a video game, so we can probably sacrifice a bit of it. Then we have to smash them together. Usually what you do, you just take Newton's, it's all Newton, Newton's equations of motion in something called Euler's method in numerical analysis, where you basically calculate the velocity at the next time step in your simulation as the velocity at the previous time steps plus the acceleration plus some difference in time between those 2 time steps, and then the same for the position. We didn't actually use this one because this one leaks energy and doesn't conserve energy and isn't really stable. So we use something called the Leapfrog method, which does something called a drift kick drift thing, where it kind of moves the velocity in a half step then takes a full step in the position, recalculates the acceleration, and then moves the velocity in. Why do we do this? Like I said before, Euler's method doesn't actually conserve energy and isn't really stable. Leapfrog solves all of that, so we use that instead. Here's a video of the actual simulation. So basically, we just redo this over and over and over, thousands of times. Basically, we calculate the acceleration felt by every single particle at every single time step, and then we just take a step. Do it again, take a step. And we press play, and it basically just moves along. It's about 1.5 minutes, so we'll just go slowly through it. I'll see if my notes are telling me to say anything. Yeah, it is. So there's about 24,000 particles in this simulation. Took about an hour to run fully. This is actually the simulation that is running on the computers behind you. If you go into them and press M, you will see the star map, and you will see a certain time frame of this simulation. I'm not going to tell you which time frame, but it is there, and we're actually getting quite close to it. It is somewhere around there. And you see that you get these really funny and interesting patterns. There's a smash that happens there. And around there, I think somewhere at that point, we pause the simulation and we say, this is our universe. And that's what we do. We pick a nice time step. And personally, I find that it looks pretty nice. So you see that we have like you see the 3 bulges that were there. You see there's like a weird funnel that kind of ripped everything out of the plane of the galaxy. You have a tail. You have a bunch of cool structures. And like I said, you can actually look at this map in the game right now, or after the lecture or presentation. Okay, so then there's the stuff inside the solar systems, basically generating content, stuff for you guys to do when you visit those solar systems. And for all the points in the simulation, they actually had a mass, a distinct mass that was sampled from something called an initial mass function, which is really just a probability function or density function that tells us the initial mass of stars in galaxies and in the universe. You heard that I said initial, so it isn't actually because masses of stars evolve over time, so it isn't completely realistic to use that, but we're going to use it anyway. And we actually know from astrophysical observations and stellar modeling that there are certain scaling laws that basically tell us how different attributes and properties of stars relate to other attributes. For example, one of those is that the luminosity of stars scales as the mass of the star to the 4th power. And then you have different scaling laws for the radius and temperature and stuff like that. So we basically just create like a procedural generation script that takes in the mass of the star and then generates the rest of the properties, which, and I list some of them here, like metallicity, the age of the star, the radius, luminosity, temperature, spectral type, and so on. Whatever we need for the game to use. Then we generate a number of planets to place around it. The simulation that I showed you before the same code could actually be used to generate planets, as in you could think about a star that has a protoplanetary disk of dust and gas that is orbiting it. And slowly over time, as it rotates, the dust starts to clump together and form something called planetesimals, which are really just clumps of matter. And those basically form the planets. That is very expensive, especially if we have 24,000 systems, and that's going to take a very long time. So we didn't actually do that. We just did like a simplified version of it, where we didn't think about simulating it, but we thought that there is an initial protoplanetary disk that has a certain amount of mass, and instead of simulating and letting it clump together, I just figured, okay, I'll take a shovel and have a bucket full of the remnant mass or the mass of the protoplanetary disk, and I'll scoop a planet out of it, and I'll place it somewhere. And then I'll do that again, and I'll do it again until the bucket is empty, and now I have my planets. It takes a very short time to do that, compared to actually simulating the whole formation of planets and stuff. Then we generate properties for each planet, just like we did for the stars. They have a radius, density, orbital info, inclination of orbit, all of that, temperature, anything you can imagine, or not really anything you can imagine, but more like anything we could use to inform the game about stuff of how you guys play it. Then we generate a number of moons to place around each planet, and so on. Whatever we need to place in there. And we get some image that might look like this. This is a particular solar system somewhere in the game. It has a star, it has 2 planets. They're actually color-coded depending on their types, but I'm not going to tell you what types they are. They have some moons that have some orbits and stuff like that. Because if we have 24,000 solar systems doing this by hand, no chance, obviously, so we need some sort of generation system for it. So, what's left? As in, what's left to make this a usable universe for the game, is the question. Because technically, we've generated the universe, right? We have positions of stars, we have masses of the stars in them, we have the content around them, but there's actually nothing to do there, right? We need infrastructure, we need NPCs to fight, we need asteroids to mine, and all of that. So first part is infrastructure, which is really just a question of, like, is there any technology in the galaxy? Are there layers or leftovers of ancient civilizations that might have left stargates and stations around, or is there any active societies in it? Have they built connections or stuff like that? I'm not going to go into that. If you have questions about it, I can discuss it, but we're not going to go into it today because the keynote is starting very soon. Then there's the content, which is really just the stuff for the players to do and interact with. Like I said, asteroids, NPCs to fight, areas to fight over, which really come along with the other stuff. But I am going to end by showing you examples of how we might use all these attributes, like the reason why. Why are we even doing this? Why do we need all these procedurally generated systems that have different attributes that, do all this stuff? My favorite example, mainly just because I'm working on it these days, is content distribution, and namely natural resource distribution, as in where do the asteroids live? And if we think about it on a global scale, we can, in a sense, this could be more realistic, but I'm still going to say that this is realistic. We can create a realistic distribution of natural resources and others by, for example, using the attributes of the stars to determine where they are. So, for example, like I see here, systems that have a star with high metallicity might be more likely to have metal-rich asteroids. Stars that had a lot of remnant mass from planetary formation, as in how much sand was there left in the bucket when I was creating planets, might have more asteroid belts, stuff like that. So kind of from analyzing the attributes of the universe globally, you get the distribution of where you would expect different resources to be found. Is that fun? I hope so. But, that's basically up to the players to decide. Then, on the smaller scales, inside the solar systems, we also know that solar systems have natural resources in particular places. They're not just anywhere in the solar system. I mean, sure, they're in a lot of places, but like asteroids tend to clump in certain places in solar systems. And I really like this picture here of our old solar system, where you have Jupiter, Mars, Earth, Mercury, Venus, Sun, and then you have the asteroid belt that lies between Mars and Jupiter, and then you have the Trojans and the Greeks, which are basically asteroids that have been trapped at the L4 and L5 points of Jupiter, which are like points of gravitational equilibrium in the three-body problem of Jupiter, Sun, and thing moving around it. So we basically get informed by this, and we actually have calculated all the L4 or all the L points of all the planets in all the solar systems in our simulation. So we actually have all of this information. So a player could theoretically figure out that, like, okay, if I want this particular type of resource, I could go to a particular type of system that has a star that has some attributes, and then a planet which is really high mass, which means that it attracts more asteroids to its L4 point, things like that. That's kind of the idea, that it kind of, I don't want to say we get this information for free, but physics and astronomy basically gives us this design for us, almost. So it kind of emerges from the generation, so to speak, is kind of the idea. That's all I said, and basically that's it for now, because like I said, we have the eFrontier keynote in Norðurljós, which is right next door. I would really like for all of you to go there. We probably have time for like 2 or 3 questions, but I will be here without a mic after the keynote if you have more questions. Just I'll come here, I'll see if anyone shows up, and I'll answer your questions and so on. All right, thank you.
Anyone have any initial questions?
Have you considered doing Newton's laws of motion properly instead of underwater physics?
So I'm going to refer to CCP Wizard that is sitting in the corner behind you, because he did the full-on physics of the actual Frontier talk yesterday. I don't think we've considered that because it's so tied to gameplay, is basically my answer to that. But it would mostly be on him to decide it anyway, so I'm not going to give more of an answer.
Anybody else? Okay, in that case, why don't we all head over to the Frontier keynote, and then if you have any more questions, come back after. We've got 2 astrophysicists in the room, so come on back.